Hi everyone, I am Sam. Today we are going to talk about string theory. Imagine for a moment that you're standing in a vast library, shelves stretching endlessly in every direction, each volume brimming with stories about how our world works. You walk through aisles dedicated to gravity, to electromagnetism, to the strange and tiny realm of quantum mechanics. Now, picture trying to find a single grand story that ties all these volumes together. A single narrative that unites every force of nature under one elegant cover. For many physicists, that grand story is something called string theory. And while it's not fully written yet, the chapters that we do have are among the most fascinating in the history of ideas. To understand how we got here, we need to appreciate that for centuries, humanity has been on a quest to understand the deep and hidden laws governing the universe. We've asked ourselves, what is the world really made of? How do the particles of nature interact to create the tapestry of reality we see around us? These questions led us from the ancient Greek idea of tiny atoms to the brilliant insights of Isaac Newton's laws of motion and gravity. Newton showed us that planets orbit stars following predictable patterns. But as wondrous as Newton's laws were, they didn't explain everything. Something mysterious was lurking beneath the surface. In the early 20th century, Albert Einstein revealed a revolutionary view of gravity through his theory of general relativity, showing that massive objects curve the fabric of space and time. Meanwhile, others were uncovering the quirky behavior of tiny particles inside atoms through quantum mechanics. Each of these discoveries opened new chapters in the library, but they also made the story more complicated. By the mid-20th century, physicists faced a peculiar situation. Einstein's general relativity perfectly described the large-scale universe, the motion of planets, stars, and galaxies, and quantum mechanics explained the strange, probabilistic behavior of subatomic particles. Yet, when you tried to bring them together, they refused to cooperate. It was a bit like having two beloved stories that contradict each other's endings. Gravity seemed to speak one language, and the quantum world spoke another. And no matter how hard you tried to translate, you were left with confusion and paradox. This is where the idea of string theory begins to emerge. In the late 1960s and early 1970s, physicists were wrestling with experimental data about the particles that make up protons and neutrons. They discovered that protons and neutrons aren't truly fundamental. They're made of even smaller particles called quarks. And quarks themselves interacted via something known as the strong nuclear force, one of the four fundamental forces of nature, the others being electromagnetism, the weak nuclear force, and gravity. At the time, there seemed to be a bewildering array of these tiny particles discovered in particle accelerators. Physicists called this proliferation the particle zoo, because it felt like they were uncovering more and more exotic species without a unifying principle. A handful of theorists tried a daring approach. Instead of thinking of these particles as point-like dots, they imagined them as tiny vibrating strings, infinitesimally small loops of something more fundamental. Each type of particle would correspond to a different mode of vibration of these strings, much as different musical notes come from different vibrations of a guitar string. In the early days, though, string theory didn't catch on widely. It was complex, and it didn't immediately solve the problems people were most interested in. Many researchers moved on to more promising ideas. Yet a few stubborn pioneers kept at it. Then, something remarkable happened. Physicists realized that one particular vibration of the string resembled the properties of a particle that could carry the force of gravity, something called the graviton. Suddenly, here was a glimmer of hope, a framework that naturally included gravity at the quantum level. This was a big deal because gravity had always resisted being described in quantum terms. In other words, string theory seemed to provide a language that could speak both quantum and gravity at once, potentially unifying the whole story under one overarching principle. By the early 1980s, interest in string theory exploded. Physicists realized that by considering these minuscule strings and the ways they vibrate in higher dimensions of space, they could, in principle, weave together all the known forces in particles. But the theory demanded strange things. For one, it required extra spatial dimensions, beyond the 3 dimensions of space and 1 of time we're used to. Initially, this seemed downright bizarre. Where were these extra dimensions hiding? Some clever thinkers proposed that they might be curled up so incredibly small that we simply don't notice them. Just as a tightrope might look like a one-dimensional line from far away, but up close, ants can walk around its circumference. This idea of hidden dimensions added a layer of enchantment and mystery to the story. The universe might be far richer and more textured than we can perceive directly. String theory gradually attracted brilliant minds who refined it and explored its consequences. It encountered stumbling blocks and controversies along the way. One major leap came in the mid-1980s, known as the first superstring revolution. Physicists discovered that consistency required the introduction of something called supersymmetry, a proposed symmetry between particles of matter and particles that carry forces. Supersymmetry, if it exists, would neatly solve many theoretical puzzles, though no direct evidence of such particles has been found yet. Nevertheless, this was an important step in making the theory more coherent. Now it was called superstring theory, and it came in 5 different versions. But having 5 versions of something that aimed for a unique, unified description of everything felt awkward. In the mid-1990s, another major breakthrough occurred, dubbed the second superstring revolution. A genius physicist named Edward Witten and others showed that these 5 supposedly different string theories could actually be just different facets of a single overarching theory, which they called M-theory. This was like realizing that 5 different dialects were actually expressions of the same universal language. M-theory suggested that strings might not be the only fundamental objects. There could be higher dimensional membranes and other exotic ingredients. What M-theory precisely is remains somewhat mysterious to this day, but it provided a unifying framework that convinced many physicists they were on the right track. Of course, string theory hasn't gone without criticism. It's mathematically dense and challenging to test experimentally. It's easy to propose extra dimensions curled up at scales so tiny that no current experiment can probe them. Some have argued that without concrete predictions we can verify in the lab, string theory risks becoming more of a philosophical exercise than a scientific theory. Others say that even if direct tests remain elusive now, the mathematical beauty and consistency of the theory might lead to indirect insights. After all, many theoretical ideas start out seeming impossible to test, but future generations find clever ways to probe their consequences. One of the most surprising and beautiful developments inspired by string theory is the concept of holography. Imagine a black hole, an incredibly dense region of space where gravity is so strong that nothing, not even light, can escape once it passes a certain boundary called the event horizon. One of the long-standing puzzles in physics is to reconcile how gravity and quantum mechanics work around black holes. String theory offered a clue. Perhaps the 3-dimensional world we perceive is somehow encoded on a 2-dimensional surface, much like a hologram. This insight, known as the holographic principle, has transformed how we think about gravity in space. It suggests that the fundamental description of our universe might be simpler than we think, and that space and gravity might emerge from underlying quantum processes. This doesn't just unify our understanding, it changes how we conceive of reality itself. All this might sound fantastical, and in many ways it is. String theory posits that we do not live in a universe of point-like particles bouncing around, but rather in a cosmic symphony of vibrating strings, extra dimensions, and hidden symmetries. Yet, despite all the complexity, the core idea can be understood in a simple, intuitive way. Think of nature as a grand musical instrument. Instead of fundamental particles being little balls, they're like notes played by ultra-tiny strings. Just as a violin string can produce many different notes depending on how it's vibrated, these fundamental strings can produce many different particles depending on their modes of vibration. The difference in their vibrational patterns gives rise to the variety of particles we see. The electron might be one particular vibrational pattern, the quark another, and the graviton yet another. This musical analogy can help us understand why string theory might unify physics. Right now, we have different theories for different phenomena, quantum field theories for particles and forces, and general relativity for gravity. But if they're all just different notes played on the same type of fundamental string, then it's all one instrument. The universe's complexity emerges from a single underlying principle. That's the dream, the ultimate theory of everything, that physicists have yearned for. To appreciate the historical journey of string theory, It helps to remember that progress in theoretical physics is rarely a straight line. The path is more like a winding trail through a dense forest. Physicists stumble on clues, take wrong turns, correct themselves, and forge ahead. Initially, string theory didn't seem like it would explain gravity at all. It started out as a model for strong nuclear forces. But the theory had this hidden gem tucked inside. A vibrational mode that looked exactly like a graviton, the particle that would mediate gravity in a quantum theory. This was an enormous surprise, and it pushed the field forward. As the theory developed, it sprouted more complexity, extra dimensions, supersymmetry, multiple versions. But instead of giving up, physicists found deeper unifications, culminating in M-theory. With each major revolution, the theory gained conceptual richness. And even if some physicists roll their eyes at the lack of direct experimental evidence, it remains one of the most mathematically and intellectually rich frameworks we have. One might wonder why, after all these decades, we haven't found clear-cut evidence for string theory. Part of the reason is the scale at which these tiny strings would exist, close to what's called the Planck length, a length scale so small that it makes a proton seem gigantic by comparison. Our current particle accelerators, like the Large Hadron Collider, are nowhere near powerful enough to probe these scales directly. It's like trying to see the texture on a grain of sand from a vantage point miles away. There may be indirect signatures, like hints in the cosmic microwave background radiation, or subtle effects on how black holes behave, but these are extraordinarily challenging to measure. Still, string theory has left its mark on other areas of physics and mathematics. Its mathematical machinery has solved tough problems in pure mathematics. It has shed light on the internal workings of quantum field theories and given us new tools to understand strongly interacting particle systems. Sometimes, theories contribute to our understanding in unexpected ways, and string theory's influence has radiated outward, touching fields as diverse as cosmology, condensed matter physics, and pure math. Even if we somehow discovered tomorrow that string theory doesn't describe our universe exactly, it would still be one of the most fruitful intellectual enterprises in modern science. The narrative of string theory is also a human story. It's about passionate scientists spending decades chasing a vision of unity. We see how brilliant people, faced with the most challenging puzzles imaginable, pool their knowledge, argue intensely, and collaborate across continents. New ideas emerge that at first seem impossible to swallow. Extra dimensions, supersymmetric partners to known particles, brains that stretch and twist in higher dimensional space, and gradually become standard concepts discussed in physics journals and classrooms. It is a testament to human curiosity and perseverance. Science thrives on bold ideas, and few ideas are bolder than string theory's claim to unify everything. This story doesn't have a final chapter yet. String theory remains a work in progress. Physicists continue to refine it, to probe its mathematical structure, and to search for ways that it might connect to observable phenomena. Some are exploring the vast landscape of solutions that string theory admits, different ways of curling up those extra dimensions that could produce different low-energy physics, perhaps even explaining why we have the particular constants and particles we see. Others are trying to link string theory's deep theoretical insights about quantum gravity to the mysteries of black holes, dark matter, and the early universe. Each new insight might be another stepping stone on the way to a more complete understanding. In the meantime, we can appreciate string theory for what it is, a grand attempt to write the ultimate chapter in the story of the cosmos. It's a blend of creativity, mathematics, and physics that dares to envision reality in a way no one ever did before. Even if you never study its equations or understand every subtlety, the message it sends is one of awe and possibility. The world we see might just be the surface of a deeper truth, a melody played out on unimaginably tiny strings that sing the universe into existence. Trying to make sense of string theory can feel like stepping into a realm of science fiction. Dimensions beyond our perception, symmetries that pair known particles with unknown partners, gravitational force explained by looping strings. It's not exactly everyday fare. But if history has shown us anything, it's that nature often defies our intuitive expectations. The quantum world already showed us that particles don't behave like tiny billiard balls. Relativity taught us that time can stretch and bend. Is it really so far-fetched that the fundamental building blocks of the cosmos are tiny vibrating strings weaving together the forces of nature? This journey started with a problem: how to unify quantum mechanics and gravity. It led to a theory that not only attempts that, but also demands extra dimensions and symmetries. Along the way, it produced deep insights that might lead us to new understandings of space, time, and the fabric of reality. Some scientists look at string theory and say, "This is too complicated. Maybe we need a different approach." Others respond, "But look at the beauty, the elegance, and the possibilities." Even if it's not the final answer, it's pointing the way. In a world where experiments at the required energy scales remain out of reach, string theorists rely on consistency, mathematical elegance, and indirect evidence. They ask whether the theory leads to contradictions and whether it can reproduce known physics. So far, it's passed many logical tests. It manages to incorporate all known forces in a single structure to produce a candidate for the graviton and to offer insights that have spread into other fields. It's not perfect, and many details remain mysterious, but it's alive and evolving. We can think of string theory as an ambitious draft of the grand story of the universe. Physicists are still editing the manuscript, checking its consistency, making sure each chapter fits with the next. They're debating the right interpretation of certain passages and looking for new experiments that might confirm or refute particular plot points. Perhaps future technologies, more powerful accelerators, refined gravitational wave detectors, or novel astronomical observations will provide crucial clues. Or maybe a radical new idea will emerge, building on string theory's foundation or showing a different path entirely. For now, string theory stands as one of the most captivating attempts to unify our understanding of reality. It reminds us that science is not just about gathering facts, but also about exploring possibilities, asking daring questions, and following them wherever they lead. It's a reminder that even the most basic elements of our world, space, time, matter, energy, could have origins more subtle and poetic than we ever imagined. Ultimately, the appeal of string theory lies in its vision of harmony. It whispers that beneath the chaos of everyday life, beneath the whirling electrons, the shining stars, and the vast stretches of emptiness, there might be a simple tune playing, a single underlying principle that brings it all together. Whether or not string theory turns out to be the final answer, it has already enriched our understanding and expanded the scope of our imagination. And who knows, perhaps one day, when technology and theory have advanced far enough, we'll open that final chapter and read with astonishment how the universe, in all its complexity and wonder, emerges from the gentle vibrations of tiny cosmic strings. That's it for today. If you enjoyed the video, don't forget to hit the subscribe button. And remember, all my videos are made to be accessible to everyone, no matter your academic background. You'll be able to grasp topics like game theory, nuclear physics, behavioral economics, and so much more. Thanks for watching, and I'll see you in the next episode.